In this video, we're going to do the final example from this note. I recommend you pause the video or try the example yourself first, then follow through with the video to see if you're on the right track. You can also try the previous examples. The answer keys are included in the filled-in version of the note. The reason we're going to try this one is because you don't have a reaction provided to you for you, so you need to create a reaction equation in order to actually do this problem. So, with a precipitate form, if 50 mils of this 2.4 times 10 to the power of 3 mole per liter calcium nitrate solution is mixed with 350 mils of this 3.5 times 10 to the power of negative 2 mole per liter magnesium hydroxide solution. So essentially we have two solutions, 50 mils over here and 350 mils over here. And so when we combine them, we should have a total of 400 mils. So let's keep that in mind because remember, that's our volume 2. That's our final volume for our concentrations that we need for our precipitate. So let's go ahead and write out an equation for this. We have a solution of calcium nitrate. Calcium is +2, nitrate is -1, so this is calcium nitrate, plus magnesium hydroxide, a solution. And they're doing a double displacement reaction. So the calcium goes where the magnesium is, and the magnesium goes where the calcium is. And so we'll get magnesium nitrate plus calcium hydroxide. And we need to figure out which one of these is soluble and which one is insoluble, if any. So we'll do the magnesium nitrate first. We'll go to our solubility table, and we'll see that the nitrates, most of them are soluble. So that makes that one aqueous. So this is not a precipitate if there is one. Calcium hydroxide. Let's take a look at that. Hydroxide. Let's find hydroxides. Here we go. Alkali metals, H+, NH4+, Sr2+, Ba2+, and Tl+, they're soluble. Everything else is insoluble. So calcium is not in the soluble list, it's in the insoluble list. So because calcium is in the insoluble list, that makes our calcium hydroxide soluble. So this would be our precipitate. So what I'm going to do is I'm going to write a dissociation equation for that precipitate, and then try to find values to help me calculate the QSP. So let's go ahead and do that. So step 2, we have calcium hydroxide dissociating to form the calcium 2+ ions plus 2 hydroxides, because there's 2 hydroxides there, ions. And so we know that the QSP is going to be equal to the concentration of calcium 2+ times the concentration of OH-, but that's squared because of the 2 there. And our KSP for calcium hydroxide, let's go find that before we continue, is (5.02 times 10 to the power of -6). So our goal is going to be to find the concentration of these ions in this new solution so we can determine the QSP. So let's go tackle the calcium first. So we want to find the concentration of calcium, and the calcium comes from a calcium nitrate solution. So let's go ahead and do that. We're going to make a ice table for calcium nitrate. That forms some calcium ion, 2+, plus some nitrate, 2 of them. We don't really care about the nitrate, but we're still doing it for the sake of completion. So we're going to make a little ice table here. And the concentration of the calcium nitrate was 2.4 times 10 to the power of -3. We know this is 0 before dissolving. After dissolving, this is minus x. This is plus x. This is plus 2x. This is x. This is 2x. And this is 0. And so what we know is that this makes it so that our x, which is the concentration of our calcium, that's what we care about. We don't care about the nitrate since that's not in our precipitate, is going to be 2.4 times 10 to the power of negative 3. But remember, so that's the molarity, but remember that this is in the initial volume before mixing in 50 mils. So we need to find this in 400 mils. So we know C1V1 is equal to C2V2. Therefore, C2 is equal to C1V1 over V2. So our C2 is going to be equal to 2.4 times 10 to the power of negative 3 molar times the 0.05 liters, because that's 50 mils, over 0.4 liters, because that's 400 mils. Cancel out the liters, and we're left with molarity. So we have 2.4 times 10 to the negative 3 times 0.05 divided by 0.4, and we get 0.0003 molar in that new solution. So we can go ahead and plug that in. So now that we have our calcium, all we have left to determine is our hydroxide. So let's go ahead and make an ice table for magnesium hydroxide, because that's where the hydroxide comes from. So we'll do magnesium hydroxide, solid, make our equilibrium arrows, becomes magnesium 2 plus aqueous, plus, be careful here, 2 hydroxides, because there's 2 hydroxides in magnesium hydroxide. And we'll make a little ice table. And the concentration to begin with was 3.5 times 10 to the power of negative 2. This was 0 and 0. This is plus x. This is plus 2x. This is x. This is 2x. This is minus x. And this is 0. So we know what the x value is, but we want 2x because we have hydroxide in our precipitate. So therefore, 2x, which is the concentration of the hydroxide, is equal to 2 times 3.5 times 10 to the power of negative 2. So we have 3.5 times 10 to the power of negative 2 times 2 gives us 0.07 molar. Once again, the problem is that this is in the old volume. We need to find the new volume. So we need to do C2 is equal to C1V1 over V2. C1 is 0.07 molar. V1 is, I believe, 350 mils. That's correct. So 0.35 liters over the new volume of 0.4 liters. Cancel liters, you're left with molarity. So 0.7 times 0.35 divided by 0.4. And we get 0.06125 molar. So we can go ahead and plug that in to the equation here, 0.06125. Don't forget to square that, and you'll get, so square that, times 0.0003, 1.125 times 10 to the power of negative 6. So they look pretty close because they're both 10 to the power of negative 6. But it looks like your KSP is larger than your QSP. So QSP is smaller than your KSP. Therefore, we have an unsaturated solution. Unsaturated solution and no precipitate forms. We can verify our work by going to the filled in answer key to check if we're on the right track. We got 1.1 times 10 to the power of negative 6, QSP less than KSP, and no precipitate forms. So we're on the right track. We did the correct steps. Let's go back and just recap what we did to make sure that we understand the problem. So in this question, we mixed two solutions together, and our goal was to figure out if a precipitate would form or not. So we had to write a double displacement reaction, find the precipitate using our double displacement table, our solubility table, then make a dissociation equation for the precipitate and a QSP expression, and then find the KSP in the table so that we could eventually find the QSP to compare it to the KSP and make our conclusions. To calculate the QSP, you need to find the concentration of those ions in the precipitate in that new solution. So you have to use the compound that contributes each ion, make an ice table for each one to find the concentration of the ion. So we did it for calcium nitrate. We cared about the calcium ion because that was in calcium hydroxide. That was our X value, but this is in the old volume, so we had to find the new volume, which is the 50 mils plus the 350. We used our dilution formula to find that concentration, and we plugged it into our QSP. We then did the same process for magnesium hydroxide, but we didn't care about the magnesium. We cared about the hydroxide, which is the 2x. So be careful here. Don't forget to multiply by 2 because you're looking at 2x here. And then you still need to use your dilution formula to figure out your final concentration in the new solution. And then you can plug that in to your KSP, to your QSP expression. And don't forget that squared term there. That's important because you have two OHs. And so that results in this QSP over here, which you can compare to our KSP. This QSP was smaller than our KSP. So what that means is we have an unsaturated solution and no precipitate forms. You can still dissolve more of the magnesium, the calcium hydroxide in this solution. So even though, yes, we saw precipitate in our double displacement, there won't be a precipitation that will be occurring because there's just not a high enough concentration of the ions to result in a precipitation occurring. You need a little bit more of one, the other, or both to get you to this mark over there. If this was a lower solubility, so you had, let's say, 10 to the power of negative 7, then you would have precipitation, for example. So hopefully you're able to do all these steps to demonstrate where the different concentration come from. You should be able to do the problems, the other problems in a note. Just make sure you check your work using the filled in version or the answers that are provided on the page itself. But what's important is understanding the process and avoiding little errors like forgetting the 2x or forgetting to square based on your QSP expressions. So pay attention to those little details. Make sure you don't miss out on those. Otherwise, you will get drastically different conclusions than the ones that you should be obtaining.